carbon-13 spectrum. As I said even before, to even get some spectrum, we had to wait for Fourier transform spectrometers to be available. But even if they were available, I have this problem, in the sense that every hydrogen sitting next to carbon is going to hurt it. But every carbon sitting next to hydrogen is not going to hurt the hydrogen, because hydrogen will have a problem only in 1% of the sample. But 1% of carbon-13, which is what you are seeing, always has a problem with the hydrogen sitting next to it. It's going to be split. So what do I do? How do I take care of this problem? I'll return this quickly, but then we will come back and redo that a little later. What I do is the following. While I am recording the carbon-13 spectrum, and where is it going to come? At a frequency 1/4 of the hydrogen. So let us say if carbon is coming at 25 megahertz and hydrogen is coming at 100 megahertz. I record the 25 megahertz spectrum. At the same time that I am recording the 25 megahertz spectrum, what do? I shower the sample with 100 megahertz intense pulse. So what is that 100 megahertz intense pulse going to do for me? So here's my carbon and here's my hydrogen. This is 100 megahertz and this is 25 megahertz. I'm actually recording the spectrum of this at 25 megahertz, and just like the way I did for hydrogen. But what am I now doing? Something that's very different. What I'm doing now is, while I'm recording the spectrum, I have another source of radiation which actually corresponds to the transition between the two protons. And when that happens, what happens? This proton goes up, little while later it will come back down, but then this intense pulse is always there. So what will happen again? It will go up, and when you have this pulse which is very, very intense, what will be the population of this and this? Nearly equal. Because I'm simply shining light. Earlier I had a 20 ppm difference, but then I'm shining light and making these protons go up and come back down, and they keep cycling. Therefore, the average population in these two is going to be roughly the same. So which means that when this carbon atom turns around and looks at it, this proton is up, little bit later it's down. Because it has gone up and come down. Okay, and I keep doing this. So this fellow is actually flipping spins back and forth, flipping spins back and forth. So every time this carbon-13 looks at all the protons around, what does it see? It does not see a proton this way or this way. And we wrote all these different orientations, if you remember. But now what's happening is it sees it this way. Moments later, it's back again down because it has gone up. And little while later, it will come back down and go back up again. And therefore, it's doing this. And every proton is doing this. So every proton is actually flipping up and down all the time. So what is the average spin the carbon will see? Nothing. Then what have I done? I have simply killed that coupling. And this is called decoupling. This is called decoupling. If I did not do this, if I did not have this extra frequency making these transitions, what will the carbon-13 do? It will look at the protons around and find some of them up, some of them down, and making the actual field felt by carbon-13 different because of the spin coupling. But what I have done now is simply applied a strong radiation at the transition frequency corresponding to the proton, and therefore you will find that these protons are basically going up and down all the time while the experiment is going on, and therefore the carbon-13, when it looks around, it doesn't see any protons sitting in one fixed orientation, but it's actually seeing these protons going up and down all the time, and therefore sees an average moment of 0. If the average moment is 0, what will happen? This will return to this. I see one peak. And this is what we call as decoupling. And since I am decoupling the spins of the protons with respect to carbon, I call this as proton decoupling. So now tell me, is proton decoupling an advantage or a disadvantage? It's really an advantage because the intensity will actually get to be larger, and therefore it's actually an advantage. But sometimes you can let it couple. Why should I let it couple? Because if I let it couple, and somehow, but let's say do a very long experiment, collect data for a long period of time so that the signal to noise improves, and these 4 peaks or 5 peaks that we saw over here, 5 peaks, I am able to record that and see 5 peaks. What does that immediately tell me? That carbon has 4 hydrogens sitting on it. That can be a very useful piece of information. But if I already know that information and I'm looking for some other information, then this information becomes useless. I already know it and it is splitting the intensity. So then what do? I do proton decoupling. So I can do proton decoupling when I already know this carbon has this many protons, and all these protons are simply splitting the carbon signal and making it so small that I have a hard time even getting it. In which case, it is better for me to do proton decoupling. But if I don't do proton decoupling and I don't do it deliberately, what information am I really looking for? I'm really looking to see how many protons are there sitting on that one carbon. And that sometimes can be a very useful piece of information. So actually you do both experiments. Sometimes you do it proton decoupled, sometimes you allow the coupling to happen. So when you're giving a sample to the NMR spectrometry person, or hopefully someday in IISER we will have a situation where students will record their own NMR spectra, you will find that you will probably have decided to, okay, now I will do it with proton decoupling. After having done that, I take one more spectra with proton coupling allowed to be there, and then I compare these two. The first one, when the decoupling is going on, actually gives me the different types of carbon atoms, just like different peaks give you different types of protons. Carbon atoms, supposing I gave you, let us say, methanol. Let's take the same example. If I do a carbon 13 spectrum of this, how many peaks should I get for carbon 13? One for this carbon, one for this carbon. Two separate peaks. Because they are in different environments and therefore will have different chemical shifts. Again, the same way I did it for hydrogen. But then, if I allow coupling to go on, what will happen to this fellow? If I allow coupling to go on, the proton will couple to this carbon 13 will couple with these three protons, and that should give me 4 peaks. The carbon 13 can also couple to this carbon, but in that I don't have to worry, because what are the probability that two carbons sitting next to each other are both carbon 13s? Very small probability, right? If I have 10,000 white socks and 10 blue socks, I put 2 at random, what's the probability I'm going to get 2 blue? Hardly any. Therefore, in a given molecule, this and this both being carbon 13 is really, really small. 0.1 into 0.1, and 0.01 into 0.0, nothing. So I don't have to worry about that. But there could be a 3-bond coupling between this carbon and this hydrogen. So you can see it can be quite complicated. But if I do proton decoupling, how many peaks should I get? One for this, one for this. That's it. And therefore, if I do a C13 NMR spectrum, if I do a proton NMR spectrum, do proton decoupling for the carbon 13, don't do proton decoupling for the carbon 13, you are actually sitting on important pieces of structural evidence for the molecule. But of course, sometimes even that is not enough and you have to pay some more tricks on it. But at this point in time, you already see that the power of NMR is so good that I can actually start getting very useful and very important structural information on these systems. So that's basically what it is. Tomorrow what we will do is, we will, on Wednesday, we will look at a little more for this carbon, see how we can look at a few spectra and analyze it. And on Wednesday what I will do is I will start with these spectra, because every day I bring this here thinking I can show it to you, I'm not doing it. On Wednesday we will do it. And of course also we're going to look at these in the help session for those people who want it. And then we will get into some introductions of ESR. Is there a possibility of one month? I don't want to do anything on Friday and have it for the exam. On Friday I'm going to summarize the whole course. So, and maybe discuss issues that you have and what I expect from you in exam and so on. That's basically what I'm going to discuss on Friday. Of course, there's no license for you to keep away. Please do come on Friday. But then, if I can have one more class, it will really help me. If we can have it on Wednesday. Pardon? How about Wednesday? We have one on 5 o'clock, but I just want one more so that I don't have to do anything on Friday. Wednesday morning? Thursday? What time? How about Thursday? We have one class.